Aren't you enjoying this story time of TLC? Because I know that I am. Well, probably not. And you're probably tired of listening to me talk about it too. But, we're almost done. We probably won't finish in this video, but we're almost there. So bear with me. Go ahead and kick out these last couple of videos, and you'll be okay. You'll be finished. And no more TLC, hopefully, maybe for the rest of your life. But if you're unlucky, you'll be one of those few that will be running it every day, and you'll be stuck in TLC fairyland from here on out. All right, so we've talked about plates. We've talked about basically the stationary phases, and we've talked about the mobile phases, and we've talked about indicators that go onto the plates. But at no point in time have we talked about what happens after the spot gets developed, right? Okay, so not too much work is left. Once you develop a plate, and you mark your mobile phase front, and you mark where your origin is at, and this is where you've spotted, and let's say I get a spot that's right here. Now, what do I do with it? You just don't compare how high the spot has traveled. That's not what you do. There's actually a little bit of math that you've got to accomplish when you process these TLC plates. And this little bit of math is going to be pretty important. So all this time, we've talked about the spot getting held back. So the definition of getting held back is called retard. You are retarding the spots. Now, you might laugh and you might snicker, but that's really what the definition is. So we are retarding the spots, and then we're going to measure the retardation. And that's why we call this the retardation factor. That's the proper name of this calculation. So the retardation factor, well, because we don't want people to make fun of us too much, we use a capital R, and then for factor, we use a lowercase f. So we need to learn how to calculate retardation factor, or RF, of my spot. How much did it get held back, right? Pretty simple calculation. I take one number and I divide it by the other. Okay, well, what are the two numbers that I need? Well, over here on the TLC plate, I'm basically going to literally take a ruler and I'm going to measure the distance from my starting origin to the mobile phase front. That is why that's very important. If you let your TLC plate develop too long, the mobile phase front goes up here to the top, but everything else is going to kind of move. And you can't get a proper reading of a mobile phase front. And that's why you have to pull the TLC plate out early every time. So that way you can get this proper distance. Very, very important in TLC development. So I'm going to call this the distance of the mobile phase front, or the distance traveled by the solvent, whichever one you like better. So that's one measurement I have to make. The second measurement that I'm going to make is how far did the spot travel. So I'm going to take my ruler and I'm going to start down here at the point of origin, and I'm going to measure how far the spot went up. And this will be the distance of my spot. Now, the question here that people have is, well, what do I do with my spot? Do I measure the center of the spot? Do I measure the top of the spot? Do I measure the bottom of the spot? Because that really is going to play a factor in what my retardation factor is going to be. And the answer here is it doesn't matter. You just want to be consistent. Be consistent with your measurements. So if you do the top one, do the top one every single time. If you do the bottom every single time. If you do the center every time. The issue here, though, is what if we don't end up with a spot? What if we end up with a smear? Now we have a problem, because do I measure the bottom, or do I measure the top, or do I kind of do somewhere in the middle? Well, that's up for you to decide. And quite honestly, if it was me, I would not be happy with the smear, and I would completely redevelop the TLC plate, and I would maybe put less compound on it this time, and hopefully I will end up with a cleaner spot or a circle that I could measure. That would not be acceptable to me. I would want to redo it, just because personally, deep down, I know it's wrong. Okay, so once I do these two distances, I then take those measurements and then I'm going to divide them. That's the only thing that I have to do. So up here at the very top, I'm going to take the distance of my spot, and then I'm going to take the distance of the solvent or the mobile phase front, and I divide the two numbers by each other. This number will always be bigger because that's your mobile phase front. That makes sense, right? So if this number is always bigger, then that means your RF will always be smaller than 1. There's no way it can be greater than 1. In order for it to be greater than 1, that means that your spot has to travel further than the mobile phase front. And that, we know, is not plausible. That doesn't make any sense at all. The mobile phase is the one that carries the spot in the first place. So how can the spot travel further than the actual carrier? It's not going to happen. If you get an RF that's greater than 1, that means that you've switched these two numbers around, and you need to flip them, and you need to redo the calculation. But your RF should always be less than 1. Okay? Now let's take two examples down here at the very bottom, and let's relate this to something that we've talked about earlier. Let's say that I've got two plates, and I've spotted a sample on each one. Here is my mobile phase line up at the top. I've marked them. I've developed my plate. I see the spots, and now the spot is showing up on the plate. And this one's here, and this one's here. All right, well, I'm going to measure, and I'm just going to make up some of these numbers. So I'm going to measure the distance from the origin to the top, and let's say that I get 10 centimeters on that one, and I get 10 centimeters on this one. And then let's say I measure the distance that my spot has traveled up the plate, right? So this one didn't travel up as much. We now know that that's probably a polar compound because it didn't go far up the plate. It stuck with the stationary phase. The stationary phase is polar. My mobile phase is probably more non-polar because we always have those complements. So there's my spot. Didn't travel far. I'm going to say it's somewhat polar at least. And I measure the distance. And that distance, let's say, is 3 centimeters. And then over here, this spot traveled more. That means it's not hanging out with the stationary phase. That means it's not hanging out with the silica and the alumina. That means it's not probably polar. It's more non-polar in nature compared to the first one at least. And this one traveled up further, and let's say that this one went up 8 centimeters. Typically, I measure in centimeters. Well, then I'm going to come over and I'm going to calculate an RF for each one of these. And what I do is that I take the distance that the spots traveled, 3, and I divide it by the distance that the mobile phases traveled, and that's 10. So 3 divided by 10, that's 0.3. There's my RF for compound A. I do the same thing over with my second one. I take the distance that the spot traveled, 8. I divide it by the distance of the mobile phase, that's 10. Well, that basically is a 0.8 RF. So now I can relate RF numbers to polarity. The RFs that are lower, such as this one, if I have a very low RF, that means that my compound is probably polar. If I have a high RF, that means that my compound is probably nonpolar. And that's the relationship between the two. Very high RF numbers mean very high on the plate. Keep that in mind. High RF numbers mean high on the plate. And if they're high on the plate, then that means they're probably nonpolar because it's not liking the stationary phase that you've chosen. And again, 70 to 80% of the time, it's silica. So most of the time, it's a polar stationary phase. So that's how we calculate RF. And we can calculate the RFs of all the compounds, all the spots. So for instance, if I have another spot that shows up on the plate here, that's okay. I just do the same distance because it started at the same spot, and then I just measure from the origin line to the second spot, and that, let's say, would be 6 centimeters. Well, I can do an RF of that component, 6 over 10, and that's equal to 0.6. Not a big deal at all. You treat them separately. It's okay. So if you have 15 spots, you'll have 15 RF values that you'll have to report. Okay, now what's the purpose of the RFs? Well, this gives us a number. This calculation provides us a way that we can do a known and an unknown. So let's say that I develop 3 plates this time, and here's my origin, and there's where my mobile phase has stopped. And here we have that one, and then we have this one that's maybe a little higher, and then let's say that we've got this one again. Well, just by visually looking at it, I can probably tell that the A and the C are similar, right? I cannot maybe say they're identical to each other, because maybe these RFs are close but not close enough. But visually looking at them, I'm going to say that A looks a lot like C. Right? It looks like they've traveled up the spot or up the plate about the same distance. B's a little bit further up, so B is a completely different compound. Well, what I can do is I can calculate an RF of each one of these. I can calculate an RF of A, of B, and of C. And if the RF of A is equal to the RF of B, then sure enough, they are the same. If they are not equal, then they are not the same. And in this case, they will not be equal. My A and my B are completely different. One's further up the plate than the other, but now I have a mathematical representation of what I see. I can calculate a value, and that value can be used to compare other plates to. And that's what we do in the TLC world. So we identify the unknowns based on RF numbers. Okay? So let's say that this is not a sample really, but let's say that this is a standard. And I know what that standard is. And let's say that this standard maybe is aspirin. And I put aspirin onto this plate and I develop it. And let's say that I'm given a sample in the laboratory, maybe 2 different ones. I get B and I get C, and I run them. Well, I know that B is not aspirin because that retention factor or retardation factor is not the same as what my standard was. For C, it's pretty close. And when I calculate my RF, it won't be identical, but it'll be close. And because of that, I can kind of say that my RF of C matches the RF of the aspirin standard that I ran. And due to that, the sample is probably aspirin. That's what we do in TLC. And that's really all that we do in TLC. Remember, TLC qualitates. And that's what we've just done. We've qualitated it. We've told you what is present and what is not. The TLC plates do not traditionally quantitate. That means I've identified that aspirin is the unknown that was provided. I don't know how much. I don't know the concentration, but I know that C is probably aspirin. That's qualifying. Quantifying would be figuring out how much of that is actually present. And that's where the other chromatography instrumentation comes into play. So, TLC, pretty simple, pretty cheap, pretty quick. I can qualitate it, but I can't quantitate it. All right, so that's where this video is going to stop. And we probably have one or two more videos that's up the path. So no big deal. I think that we'll get through these pretty quick. And I think that you'll be very happy when it's over.